Hello, everyone. Thank you so much for joining us. I welcome all of you. My name is Armagan Al-Haq. I'm the Managing Director with the Waterloo Institute for Sustainable Energy at University of Waterloo. Before I begin, I would like to do the territorial acknowledgement. The University of Waterloo acknowledges that much of our work takes place on the traditional territory of the neutral Anishinaabe and Haudenosaunee peoples. Our main campus is situated on the Haldimand Tract, the land granted to the Six Nations that includes 6 miles on each side of the Grand River. Our active work toward reconciliation takes place across our campuses through research, learning, teaching, and community building, and is centralized within the Office of Indigenous Relations. It is my honor and privilege to introduce our guest speaker for today, Jen Lee. He received his PhD degree at Cardiff University. He is now an associate professor at Technical University of Denmark. His research interests include control and protection of DC technologies, offshore wind, offshore energy islands, and power electronic-based power systems. He has won numerous research awards when it comes to his professional work. He is now a steering committee member of CIGRE Denmark NGN, a member of CIGRE Working Group B496, and a member of the IEEE PELS Publicity Committee. Ladies and gentlemen, please put your hands together for Professor Lee.
Okay, thank you very much for your introduction. And I'm very happy to be invited by Saha to be here. And this is my first time to Canada and from another cold place from Denmark. I will present where is Denmark now. So my today's work is offshore wind in Europe and HVDC technology. How can we use this technique to achieve this 100% renewable energy-based power system? So first of all, I can briefly, in detail, introduce myself. I received my BEng, Bachelor of Engineering in China. That is Northeast Electric Power University. You can see from the name of my university, it's famous for electric power energy system. And it's also in Northeast China. So its winter time is -20, -30 even. So it's cold compared to here, it's not very different. Okay, so I can use to this cold weather. And then this is the graduation day of my bachelor co-education day. After that, I went to Singapore, which is positive 30 or 40 degree hot place in Singapore. Nanyang Technological University. I did my master there, working in this power engineering. It's the same like this power system. And this is the global launch of this university, NTU, so students can celebrate their events there. After that, I luckily got this Marie Curie position like Saha, when we met together in the same project called MEDAL. And the university was Cardiff University, which is the capital city of Wales in the UK. And this is the view of Cardiff Bay. So it's a very nice and also a tiny city. And this is my PhD graduation day. After my PhD, I also continued my postdoc at Cardiff University for 4 years. And then I got this position at DTU as an associate professor, working on the same topic, offshore energy and the control and protection of HVDC. Now I have been at DTU for 2.5 years. To give you some idea about the DTU, so from this global map, you can see Denmark is a very small country. It has now only 5.8 million population. At DTU, if you know it, in most of the cases, you may know this DTU, but the English title is this Technical University of Denmark. But this is DTU, is this Danish words. And actually, if you speak in Danish, this is DTU. Yes. And in Denmark, we have the main campus are these 3. Lumbu, it's not English, it's Lumbu. And Ballup and the Riso campus. So I'm in between this Ballup campus. Each other is 10 kilometers and 14 kilometers. And this is the city center of Copenhagen. So DTU is not locating in the city center. You need to take bus for 40 minutes, 50 minutes to the city center. These are the views of these 3 campuses. This is the main building. It's called 101, DTU 101, all the administrative things, some student activities, the library, and the canteen. The biggest canteen is in this building. And this is Ballup campus, is my campus. And that is the most famous one, DTU Wind. Now it's DTU Wind Energy in Riso. So they have these wind turbines from Vestas, from Ørsted, and also Siemens. Now they have this national wind basement and test center in this campus. now. This is a view of our campus. You can see this PV panel. I will show it later in another slides. This is the whole building. From this terminal to the other terminal is 600 meters. So you can walk a lot, but it's just only 2 or 3 floors. This is our group. It's called Energy Technology and Computer Science. It's like here, ECE. But before last year, it was only this Energy Technology and Computer Science. There are 2 different sessions, but we merged that together. So the first line is the staffs in this Energy Technology. We work on this electric power system. The other 2 lines are the professors and academic staffs working in this computer science. For research topics, we are working on this machine learning, cybersecurity, IT, and also this energy system, especially this microgrids, power system, energy island. And these are some topics we are working. For this energy technology, we have 3 labs. One is this power electronics lab. Now we have 4 10 kilovolts inverters. We have the DC bus bar and also the AC bus bar. So if you want to do some tests with this multi-inverter interaction, some operation and control, we can do it on this. This is the future work. We have already set up this platform for these converters, but this real-time simulation connecting with them is not ready. But we are planning to do that. And that is the PV panel you have seen from the other GIF figure. We plan to connect this PV panel, connect to this grid, and also some other storage battery for the bachelor student project. We can combine them all together as a microgrid and to do some tests. And then another lab is this electrical machine and drive labs. We have this synchronous machine. This is mainly for teaching, and this control is from ABB. There are also some small inverters and the drive stuffs. It's not in this picture, but there are some platforms. I'm taking over this power system protection lab at DTU in the main campus, and here we only have these 2 courses for protection. We have some relays from Siemens, but they are all conventional AC system relay, protecting the AC system, bus bar protection, pilot protection, transformer protection. And we also have this test rig. This is the Omicron. We can generate the signal and to do some tests with this hardware in the loop for the student project. For research purpose, I'm working on this fault protection for HVDC, but this is for AC only. So I cannot do it with my research, but it's mainly for teaching and for some companies' tests and also some master or bachelor programs. Yes. Now let's focus on my topics of this presentation. It's not very detailed, specific technical research issues, just only the broad picture of this offshore and HVDC in Europe. So first part is this driving force. So why we need this HVDC and wind? Because we want to achieve this net zero emission. And in the Europe, the UK is the first country, the most important economic in the world, major economic in the world, launched this 2050 net zero emission. So this is net zero emission means that you are producing carbon and you are consuming some carbon, for example, in the forest, or you have some carbon capture technique. And EU's target is higher than this net zero emission. Climate neutral means that human beings' activity is not affecting the climate. This is much higher. And also for other economics, for example, China, they want to achieve this carbon peak by 2030 and carbon neutral by 2060. The reason is that they are still booming the economic. So the emission of the carbon dioxide is still a lot. So by 2030, they can reach the peak and then decline. But actually, we cannot achieve this net zero emission because this consumption is still too high. So for example, in the future, we have this carbon tax. So for example, Brazil, they have a lot of forests, Amazon forests. We can treat this carbon tax and then to achieve this carbon neutral. So these are the difference. And India is going to achieve it by 2070. So how to achieve it? To use renewable energy. And the EU has made a lot of efforts on this. So by 2030, at least 55% cut greenhouse compared to 1990s. And now we have Trump. So we don't know what will happen in the US. Maybe they will quit this Paris Protocol again. For wind in Europe, every year this, which is the organization, the wind energy. Yes, in Europe, every year in February, they will launch this new report every year. So I'm keep tracking these reports and also updating these slides. Now in EU, offshore and onshore, total is 272 gigawatts. And you can see the total power consumption from this wind, the share is increasing. But we want to achieve this 100%. It's still quite low. But if you check the total electricity consumption, you can see the total consumption is declining. So actually, this percentage is increasing. They are compensating. Because recent years, this economic is not very good. So the total electricity consumption is not too high and also declining. That's the reason this share of this renewable energy is increasing. Originally, this is 28 countries. Since 2016, EU becomes this independent. We say this is offline or off-grid operation. And now it's 27 plus UK. So you can see they are far away to go to achieve this 100% renewable energy. In Europe, the weather is not very good. For example, in Denmark, it's always cloudy. So the PV is not too many compared to this wind. I think you are in this ECE department, you know why we need to use this renewable energy. But why we use offshore? Because the wind speed is higher and it's much more stable. So we can use coal or gas because they are controllable. So we can start up or shut down this power plant quickly. But for this wind, we cannot control them. We have this problem of intermittence. So if we build this offshore wind farm in the sea, so we can have higher output and a stable output. So this is good for our power system engineer. But the problem is that we have so many disadvantages. The cost is still very high, and also this reliability, the manufacturing difficulty is much higher compared to the onshore one. So all these components should be redesigned for the harsh environment in the sea. Okay. And also in Europe, the land is very limited. So we want to build it in the sea because that area is free. Even though we have some fishing area, so somehow we can avoid this area to find one location to build up this offshore wind. And we want to achieve this 100% renewable energy net zero emission. If we build a lot of wind turbine, we also consume power and produce this carbon. So based on this Danish Minister of Energy, they say, okay, now about 90% materials can be reused. And also after half year or 1 year, we can achieve this carbon neutral. Means that the energy produced by this wind turbine equivalent to the coal or gas consumed to generate the same electricity, this one can be neutral. Okay, so in this way we can have this whole lifetime neutral of carbon. Okay, and also here this is the data. Only 5% of the global consumption is from wind. So you can see we have very good opportunity and a lot of challenges for us to increase it. So how can we grab the power from the offshore to the onshore? So conventionally, we are using AC, the alternating current. But if you know our power system, if you have attended this power system analysis course, we know that if we have two terminals, two machines, we have this equation P equals to V1 times V2 divided by X and times theta. So if this X, the impedance of this cable, especially for these submarine cables, the X is too large, so this P will be reduced. So we cannot transfer as much power as possible we want. So we have the transfer limitation of AC. So how can we solve it? We can use this method for this Housing 1 project. We put this reactive power compensation station in between. So this is compensation. We can reduce that X and then increase this distance. This distance is over 100 kilometers. Before 2023, this was the largest one in the world. The Housing 2 now from last year is the largest one. It used 170 Siemens Gamesa 7 megawatts wind turbine. The reason they use that in the UK is that they assume that this HVDC is not too mature. So we are still relying on this AC one because this has been used for many decades. It's much more mature and reliable, even though we increase the cost somehow. Okay. Another way is to convert from this AC, this sine wave, to DC. So if you read some reports for this offshore application, if this distance is over the 80 kilometers or 100 kilometers, DC is better in terms of the cost, the losses, and the control flexibility. And then we convert back to AC again to supply the conventional AC system. So we convert from AC to DC and DC to AC again. So we need to use this large HVDC converter station in the sea and also onshore. That is the main cause of this HVDC, high voltage direct current. But this is become maturing. When we did our PhD since 2013 and our Bible project, there are very limited HVDC-based offshore wind farm, all AC-based, short distance, close to the onshore grid. But now, in the past years, we have witnessed this increase and the development of this field. So there are many projects in Europe. For example, this is the ongoing one with UK and Morocco. They want to build 3,008 kilometers HVDC link from Morocco to UK through these submarine cables. So this is crazy idea. But originally, there was another one called Sun Cable from Australia to Singapore. It will be more than 4,000 kilometers. But this one is postponed already. But this one is still ongoing. Some of our friends are working for this consultancy company and the National Grid UK. They are still working on these projects. Yes. And then some cases in Europe. UK, this is the largest market in the world of offshore energy system. So since 1990s, they launched this round 1, 2, 3 scheme. So each round is 10 years. Start to build these pilot wind turbines on the seabed and also small wind turbines for offshore wind application. And then gradually increase distance by 2000. They already have some long distance offshore AC-based offshore wind farm. So they want to achieve this net zero. So they need to build a lot of wind turbine. The final goal is by 2030 will be 50 gigawatts. But by 2030 is 50 gigawatts. But 2050 will be 140 gigawatts. But the current state is only 14. You can see more than 10 times should be done in the next 2 decades. And also before he stepped on, they say, okay, our offshore wind should supply all the houses in the UK. Okay. And then Germany is interesting because in the north part, they have a lot of renewable energy, especially this offshore wind. But the load is in source. So they have the requirement from north to transfer the power to south part. So they can use these HVDC links. So they have some plans to build this HVDC corridor. And in the long term, they will have this meshed HVDC grid. But as I mentioned, they have no lands. So one method is to do this AC to DC conversion. So originally, this is a tower with 2 circuits, 380 kilowatts AC, alternative current. And the lower one are 2 circuits of this 110 kilowatts. But they have no lands, so they have no corridor. They convert from AC to DC because this AC have this skin effect. So the current will not inside of the cable, the transmission line. But if you convert to DC, the power, the current density inside of this cable or transmission line will be higher than AC. So in this way, we can increase the capacity of transfer. But this project, this UltraNet, was planned in 2013 when I started my PhD. But until now, it's not commissioned yet. So they promised to be commissioned in 2026, okay, 2 years more. And then France and Spain, this is one example in the early stage. For this project, we have 2 gigawatts transmission requirement. But at that moment, this HVDC cable, we cannot reach more than 500 kilowatts. So in this way, they built 2 320 kilowatts cables in parallel operation. But now we can have this bipolar configuration. Directly use one pole, another pole, can remove the other 2 poles. So we can reduce the cost. But at that moment, that was challenging. And this was the first AC system embedded HVDC links. So you can see this is not connecting from this offshore wind farm or renewable energy, PV or wind. They are embedded between 2 AC grids. Yes. Denmark, yes. You can see this is the Denmark's grid. If you search this Energinet online, you can find it. This figure is in real time. You can see the real-time power transfer between each other countries. So in Denmark, we want to achieve this 100% renewable energy by 2050. Okay, but Denmark is a small country. The total installed capacity is only 18.8 gigawatts in last year. So it's very small. Now we already achieved this more than 60% installation from wind. So from this report from IEA, International Energy Association, they say, okay, Denmark is reaching to this phase 5. So we already achieved very high level of the renewable energy penetration. The reason is that this small country is a kind of big microgrid. They have interconnections between other neighboring countries. In this case, if there are some emergency support or fluctuation of the wind, we can use this HVDC's fast control to mitigate this mitigation or compensate this power requirement. Also, we can also use these economic methods. Means, for example, if the wind is too strong, we have too many output from the wind, and then the electricity bill can be negative, and the customer can start use a lot of their loads to compensate this power imbalance. Yes. This is the link called Viking Link between Denmark and UK. And this is the roadmap of this. Now this is the longest one with submarine cable of MMC-based HVDC. Submarine cable is more than 600 kilometers, and also some onshore cables at the two countries. So in total, it's more than 700 kilometers. I think I have some figures. Yes, here. In my course, we organized this visit to this Viking Link. At that moment, it was not commissioned. That's the reason we have the chance to get into the converter station valve hall. So there is no electricity at that moment. Even we can touch the devices. So when I start this course and organize this visit, I asked the student to ask them, the chief engineer or some staff there, why we need this link between UK and Denmark. And the chief engineer said, because Denmark's electric bill is lower than UK. So we can sell electricity to UK. We can earn some money. And also Denmark has such high renewable energy penetration, we can mitigate this fluctuation from wind. And also we asked if we have this support from UK to Denmark. Yes, the answer is yes. We can do this power reversal from UK to Denmark if we have some emergency support or any requirement. This energy island, I'll talk about in detail later, but this one was proposed by this Danish parliament by 2020. They want to build this so-called offshore energy islands. They want to build two, actually. One is in this physical Bornholm island. The other is this artificial offshore energy island here. In the long term, they plan to build 10 gigawatts. And Energinet is the company who in charge of this construction. But I communicate with this staff from them. They say it's not us want to build this. It's the politician, the government want to do that. And in Denmark, there's Energinet. They have no researchers there. There is no research center or research institution inside the company. So since 2020, they recruit a lot of PhD and postdocs focusing on this. And the total cost of all this project is 20 billion kroners, Danish kroners, divided by 5. So that will be $40 billion here. Yes, a lot of money. And this will be the largest construction projects in Denmark's history. Yes, but now they already postponed this because this is much more beyond the budget. But the real island, the Bornholm Island, is still ongoing. Okay. I'll talk about this later. Yes, this is the link between UK, and the next logic step is to interconnect these links together to have this meshed. Because point-to-point link, if we have a fault here, we will lose the power transmission. But if we have a meshed grid, we lost one line, the power somehow can still transfer to the other grid or the other parts of the system. So we can increase this control, protection, and also the flexibility of the system by using this HVDC grid. And there are some other regions of this kind of DC grid. Also, the small circles are this energy island as well. We can have large scale North Sea DC grid. Okay. We can also say this can be a kind of super grid. But this super grid is not this kind of super grid. This is just a name proposed by 1990s. Okay. In the Europe, the backbone AC transmission system, 400 kilowatts AC, takes 8 decades. So it's long period. So for DC, we also need to spend a long time as well. Also, this name is Supergrid. There was one organization called Supergrid, Friends of Supergrids. But now this company that's consulting is already changing the name, Friends of Supergrid. They changed the Friends of Sustainable Grid. So this concept is not used anymore. So they plan to do what? To transfer the solar energy through HVDC to Europe, and also many offshore wind farms in North Sea. You can see there are some motors here, means that in Norway, more than 90% power is generated by this hydropower plant from water. So for water, you can just spend 3 minutes to start up the power plant or shut down. So this kind of power generation from hydrogen power plant, not hydrogen, what's that? Pump plant, hydropower plant, sorry. Hydropower plant is very fast and flexible to control. So this is a kind of energy storage who can also compensate this fluctuation, intermittence, yes, uncertainties. So in this way, we can have this very large scale DC grid. Yes. So we have the ideas. So how can we do it? There are many challenges. For example, this, if you do this, why this cost is very high, you need to send some people through the helicopter or the boat to fix any problems there. Okay. And these blades and all this construction, for example, if you rent this construction vehicle, suddenly there's a storm or raining, you need to stop it. So one day you lose maybe hundreds euros, 100,000 euros one day. So there's other challenge, and the cost is very high. I remember I read this report from Siemens. Maybe by 2030, the cost will be lower or matching the same one for the onshore wind turbine. So how can we achieve that? Because we can build this giant wind turbine. So I'll show you that housing one, we use 7 megawatts wind turbine, single wind turbine. But now in Europe, Vestas can now build this 15 megawatts single wind turbine, and also the Siemens Gamesa. So you can see this diameter is about 200 meters. Yes, very tall. In this case, for example, originally you built 1 turbine, 2 turbines equals to 1. So you save some money for the construction, for the maintenance. The more you combine them in series or parallel, the higher possibility you lose them, because there are always failures in the component. So in this way, we can reduce the cost. This is news, I read it recently, HVDC newsletter. In China now, they already have a company called Dongfang Electric. They produce this 26 megawatts wind turbine, single turbine, super giant wind turbine. This is really hot news. Yes. But I don't know when they will put it in the system for operation. Yes. These are the data from these 2 companies, Siemens Gamesa and Vestas. Yes, very high, more than 200 meters. Yes, this is Denmark. This is in Danish. I don't know how to read them. This is the world's first offshore wind park. It's a very small park. Only this turbines. It's not meshed grid. Only this ring is a string. And when we're there, you were not there, right? During that visit project? Yes. So on that day, we have this Marie Curie project assembly meeting. On that day, we went to this offshore wind farm, and everybody climbed to the top. In that days, everybody's Facebook is this selfie. Yes. So you can see this one here. You can see that on the top, the wind is very, very strong. And by 1990s, you can see the data. I just took that photo because I want to remember this. This single turbine is just 2 megawatts. So you can see in the past decades, the technology developed very fast, already reaching even 26 megawatts single turbine. Yes. Here. Yes, if you enter the inside of this column, you can see this climbing. About 10 meters, they will have this hole, and then this plate, and they will rotate by 90 degree or 180 degree, just in case you're not falling down from top to the bottom. Okay, so that is the technical know-how. If you don't work there, you never know these kind of things. And this our team, that is a DTU resource campus. That's the wind turbine. And in this Marie Curie projects, now everybody here, there are figures in this field, HVDC and offshore wind. Someone already, Arta is not in this photo. He is the senior vice president of Siemens Gamesa in Spain. Some of Kevin is now senior engineer, and JC senior engineer in Hitachi. He's in Germany. He's in Denmark, and Mark is the supervisor at UPC. April is also one principal engineer at Vistas, and TB is now this associate of WSP, a consultancy company. For HVDC, we have 2 technologies. One is called conventional one, line current based. So you can see there are many harmonics. They are not fully controlled. You can only trigger it, but you cannot shut it down. It can only be shut down once the current flow rate becomes 0. So it has many disadvantages, but it's very mature. Okay. But recently, since 1990s, by that professor from McGill University, yes, he proposes VIC voltage source based using this so-called IGBT, this new switch. This one is fully controlled, can be shut down and turn on, okay, by your control. And then by 2003 or 2002, a German professor developed this so-called modular multi-level converter, using this kind of concept to have small modules. Each module can produce one small voltage. And then you switch in a method with your algorithm, you can produce such kind of sine wave. So imagine if you have 200 submodules, it will become very smooth AC wave. But for this kind of LCC, you will use a large switch yard and also the AC filter yard. This one? Line commuted converter or current source converter. Okay. I will continue. Okay, and this is the development of this market. The highest voltage level and capacity we can achieve in the market. So for the LCC, we already achieved plus minus 800 kilowatts, or plus minus 1100 kilowatts. And there are some companies can produce this MMC to plus minus 640 kilowatts. And also MMC, there are some projects in China, they have this lower voltage valve and higher voltage valve to use 2 valves like the LCC one to build up the voltage to plus minus 800 kilowatts. And now ABB already produced this chip, this IGBT, 5.2 kilowatts and 3 kiloamperes. This is the largest one, the highest capacity and voltage. Yes, this is another thing called tenant. Tenant is the system operator in Netherlands and also part of Germany. They are now promoting these tenants 2 gigawatts standard offshore HVDC program. So they use this plus minus 525 kilometers, and everything will be a module. So they have the same application in everywhere, use this kind of module. The total transmission power will be about 2 gigawatts. So they say they will build more than 13 projects using this technique by 2030. Yes. DC-DC transformer. So I have mentioned we will have this DC grid in the future, but it's not like AC. We have the AC transformer which can change the voltage levels easily. But for DC, it's not that easy. That's the reason DC is not becoming the dominating electricity in the world at that moment. Edison proposed DC, but if you want to have higher voltage, you just need to build larger DC generator, but it has physical limitation. And then Tesla proposes AC transformer, we have AC. We can easily change the voltage level and have long distance transmission. But for DC, we cannot easily change it. So we need to propose this so-called DC-DC transformer or solid-state Poltronics transformer. There are many topologies in the literature, many topologies and designs, but there is no one in HVDC application, no. Because this is not a material, the cost is very high, the reliability is very low, and the fault right-through capability is low as well. Because this IGBT, these Poltronic devices, if there is a current, a fault, the current can immediately reach to more than 2 times of the standard voltage. So this can be burned. So it will be blocked to protect itself. But we have no fault right-through capability then. So these requirements and the changes are limiting this DC-DC transformer. And therefore, we have no DC grid yet in this HVDC area. And the DC protection, we also need to break up DC fault current. For AC, it's like this. So we have this so-called zero crossing. If you draw this sine wave, to do this crossing, you can use this breaker to break these fault currents, the arcs. But for DC, it's constant. Once there is a fault, the current directly go to 20, 30 kiloamperes in HVDC application. But there is no zero crossing, so the arc cannot be easily interrupted. So we propose this hybrid one or Poltronic-based one. So we use these Poltronic devices to interrupt it. But this DC breaker will be very, very expensive. ABB, now Hitachi Power, they launched this hybrid DC breaker in 2012. But until now, they didn't sell any breaker in Europe, in the world. Okay, so this is not mature yet, but this one has been used in China's Zhangbei project, and and also both of this has been used in China. And DC protection, we have fault in AC, so this transformer has this so-called impedance or reactance. This one can limit the fault current increasing, the rate of change. But for DC system, we do not have such kind of large inductance. So it's not easy to limit the fault current increasing speed. So we need to propose fast and reliable fault protection schemes. As I mentioned, DC breaker is very expensive. Then how can you reduce the cost? At the same time, achieve this fast protection. Okay. Some other techniques, we talk about AC, talk about DC. And I also mentioned this equation P equals V1, V2 divided by X. So X was related to this J omega L. So omega is the frequency of the system. So somehow if we can reduce the system frequency, for example, 50 by 3, then you can reduce this X by 3 times. And then you can increase this power transmission capability by 3 times. This is not new. In Germany, some of these railway transmission system is 50 by 3 hertz for this medium voltage. For example, 20 kilowatts AC, but in 50 by 3 hertz. But we can use the same technique for high voltage AC transmission. But the problem is that the frequency has been changed. So the AC transformer should be changed as well. So we have this low frequency AC transformer because this flux, this phi equals to related to this F. So if the frequency is reduced, you need to have a bigger column of this transformer to have the same flux. So this transformer will be newly designed. And also your breaker, you can see this is the 50 hertz, this is the 50 by 3. So the control and protection logic should be retuned and redesigned to protect such low frequency fault. Okay. But based on some of the analysis, for this low frequency one, like this, until 180 kilometers, the HVDC will be better than this. So it means that less than 180, the low frequency is much better compared to HVDC. But the problem is that this AC, the low frequency AC, is not mature, so no one wants to use it. So this is not widely applied. There is only one project in China as well. They have this demonstration, the trial application in China. One project. Yes, this is connecting to the 500 kilowatts original AC grid. Yes. Yes. Now the last part is this Danish offshore energy islands. Okay. So yes, these are the data for Denmark. 60%, more than 60% is from renewable energy. Long term is 100% climate neutral, and offshore wind is the main solution. 60% from wind, and the rest, the second largest one is from this biomass thermal power plant. Yes. Yes. They will install 6 gigawatts of wind by 2030. Install more 6 gigawatts. Okay. So this is one case, the one I show, like the HVDC case. We have some wind farms, and then we can connect these wind farms together. This is called AC collection system. And then connect one HVDC converter station, use HVDC transfer the power to the onshore grid. But if we have so many offshore wind farms, can we find another way to collect this power? For example, we can all collect these wind farms as one node, for example, 10 gigawatts together. And then through this AC bus bar, we convert it back to HVDC and send it to other neighboring countries. This concept is called energy island or energy hub. Because this is in the sea, they call it energy islands. Okay. So for example, why we want to achieve it? With this energy island, we can also use the power from the wind, because sometimes our grid cannot accept so many power. And then for the AC, we cannot storage it, because at this moment, we have no large-scale energy storage devices. So we can use the surplus power to generate this hydrogen or ammonia. So in Denmark, they call it power to X. So in this case, we can use this power to generate hydrogen, send it to the onshore, at the same time to connect it with other countries to balance the power transmission. So we can increase the power control, the flexibility, and the efficiency. There are many benefits. These are the plans. These are the two from Denmark. One is artificial, one is real. But last year and this year, this Belgium's system operator, Ilia, they proposed this energy island called Prince Elizabeth Island. They also want to build one. Okay. Then how this offshore wind energy island looks like? It's not like this. We're not building an island in the sea and insert wind turbines on the island. Actually, we are doing like this. The wind farms are in the sea, and we can collect the power in this island. Okay. And I talked with other colleagues from the EnergiNet. This one is still ongoing. The artificial one is postponed by the Danish parliament beyond the budget. So this is the real one called Bornholm Energy Island. This is a small island below Sweden, but it belongs to Denmark. In this island, they already have some renewable energy on this island, some wind turbines, some PV, and also some power to X devices there. But they still want to connect more offshore wind farms to this island. Okay. So at this stage, they are planning to build 2 or 3 gigawatts connecting to this island, use 2 separate HVDC links. Okay. And this one will be the first offshore energy island in the world. Because that artificial one has been postponed, this Elizabeth energy island will become the first artificial island in the world. They are competitive, even though this energy island will connect to Belgium in the future. Okay. Yes, this is the artificial island. You can see that the wind turbine is still in the sea. So we have these 3 gigawatts, for example, because this is too high capacity. So they need to boost up the voltage to 400 kilowatts to reduce this current. Otherwise, you have more than 10 kiloampere currents. You cannot operate in that high current. So the voltage will be very high in this AC bus bar. So they connect this AC cable to this offshore converter and convert to DC. And this is the DC bus bar because we have this multiple links. In the future, we can connect them together. And to protect the system, we have this DC breaker installed on the island. So this is DC, the power goes to other countries. So this is the concept. In the long term, it will be 10 gigawatts. From the reports from EnergyNet and DTU, they say if there's a fault occurs on this energy island, you didn't protect it properly, you will lead the whole power outage in Europe. Okay, so our duty for protection is very challenging and important. This is the original concept. I talked to the staff working at EnergyNet. They want to build even hotel in that energy island, but after calculation, this is too expensive. So they simplify like this. Only the necessary devices, power X, the hydrogen electrolyzer, or the energy storage battery will be installed there. So if you want to build this energy island, the construction of the island is one important thing, but the electrical design of the system is also very important. That is the main thing of this island, the system. So how can we build it? As I mentioned, we have the AC solution, we have DC solution. We need to pick up the best one, the optimal one. So if we build AC, it will look like this. Wind farm connect to this AC bus bar, and then send power from AC convert to DC and AC again. But we can also use DC bus bar. Okay, we can reduce the use of this transformer, the AC bus bar, directly convert from the offshore wind farm to DC and send to the onshore grid. But the DC, the protection is a problem, and also this reliability is a problem. So we can use this hybrid AC and DC. First, we have AC bus bar and then a DC bus bar. And finally, they calculate everything. They say, okay, this hybrid one will be better. Okay. In terms of this operation, in terms of control, protection, costs. This is the AC bus bar, 400 kilowatts, and plus minus 525 kilowatts DC, plus minus. Yes. And in the future, we have one energy island. We can also connect with this Denmark's energy island, with Belgium's energy island, or even in the future, UK's energy island. So we can connect them together, but the distance is too long. We cannot connect them with these AC submarine cables, but we can connect them with this DC. So that's the reason we connect them through this DC bus bar. That's the main reason. And that is the vision. If we can achieve such interconnected energy island in the North Sea, we can achieve this super grid. But at the same time, you can see there are different colors. They also generate hydrogen. So hydrogen can be used another kind of pipeline, submarine pipeline, from this energy island. The yellow one is the electricity. So we can see whether we can achieve it in next decades. Technical challenges. This is the most important thing for this energy island. The stable operation, even we have this material control for the offshore wind farm from the existing method, but for 10 gigawatts pure wind farm is still very challenging. You may have unstable operation points. You lose the stability at some operating points. So you need to solve them. And the operating condition is changing. So the wind output is changing. This operation will be affected as well. Disturbance, for example, if there's lightning, heat something, the wind turbine's output is changed. So during this dynamic and transient process, how can you control it? And also, if we use the hybrid AC/DC, they will have this coupling between AC side and DC side. And also, this can penetrate from this offshore wind farm to the onshore grids. Okay. Grid forming, this is the hottest research topic in this HVDC area. So for this AC bus bar, they are all wind farms. So how can we build up a stable voltage there? We can use this so-called grid forming control. From this HVDC converter, we generate one stable and strong, stiff AC voltage and frequency to keep operation. And if there's a disturbance, this disturbance will not affect this because we can also propose some active control against disturbance. based on this grid forming. Okay. Influence onshore, we have this fault dynamics from this frequency onshore, and this DC cannot be censored, this frequency change between the countries. So we also need to consider this frequency and the loss of this unit. If we lost one offshore wind farm due to the fault or any operation, mistrip or misoperation, we need to consider these effects. And also we connecting different countries. Each country has their own grid code. So how can we merge them together, operate stable? This inter-operation problem is a challenge. Because different countries have different requirements. And protection, grid codes, multi-vendor. We have such large-scale DC grid. We have different suppliers from Siemens, from ABB, from Hitachi, with this Ørsted. So how can we control them together stably? Because they are not sharing the data to all the system operators. So we need to figure out a way to control them together as one grid under these multi-vendor cases. Yes. And also power to X. Hydrogen is a very hot topic as well. Now, not only in this power system, in this energy system. So we need to propose the way to generate hydrogen or ammonia. And how can we transfer them from the energy island to the onshore? The pipeline, or use cargoes, ships to transfer this power. And how can we generate power on the island or distributionally generate the hydrogen? In each turbine, we put one electrolyzer, directly generate the hydrogen there, and then connect them together through this island, and then use pipeline. So there are many, many options. There is no specific solutions yet. Okay. Yes, transportation and many, many other issues. That's my presentation. Yeah, some 7 minutes left. This is thank you in Danish. Yes.
Questions?
Yes.
Thank you. Normally, we think of renewable energy as intermittent, like whether it's the sun or wind. But you didn't talk about batteries much. But in the North Sea, I take it that it's the wind. It's constantly blowing, so it's not intermittent.
We are not having this large-scale energy storage using battery in the system yet, because there's no technique right now. So that's the reason Denmark can achieve this high wind penetration is we have these interconnections. So if there are too much wind, we can send power to other countries. That's how we solve it, not using battery.
Also, it's still intermittent, but
Yes.
you want to send it away. Okay, and it was not feasible for solar power because in the very northern climates.
Yes.
Okay.
But they are still building some wind PV panels. Even in the UK in the past years, they have this transmission system operator, TSO, also the distributed network operator, DSO. The national grid is the transmission operator. They found that there are so many points, the voltage points, voltage is increasing because this PV interconnecting to this DSO, they didn't report to the TSO. So this is a problem because of this PV penetration. So in past years, they also built many PVs, even though the weather is not good.
And regarding the supergrid, if in the future we think of all cars as electric, we have a very high intensification of electricity usage, very little carbon usage, combustion. And so will it be enough? Will it have enough bandwidth in terms of energy transmitted to support a very high intensive energy electricity use society, or will it be will it need another supergrid more? Is it enough or not right now?
I think I have no specific answer for you because this is all ongoing, and you can see this challenge is still very high. The percentage is very, very low. Even though in Europe there is no DC grid yet, there is only HVDC grid for this low voltage or medium voltage DC. They have some grids, but for HVDC there is no one. There are only 3 terminals, 4 terminals in China, 2 or 3 projects only. So it may take another 2 decades. It will be our duty to answer your question to solve this problem. Yes.
And you said the energy storage is coming in the future for this?
Yes. For example, this power to X, you can assume this is a kind of long-term energy storage. because this one can be converted back power to X and also X to power. But we will lose a lot of efficiency, the power. But if there's no option, you may still need to use it. Yes. So this hydrogen application is always depends on this politician. So you need to have this support from government to use this hydrogen. Yes.
It's an intriguing concept,
Okay.
but it seems really risky to me. How do you have the island in the middle of the sea, right? And is it protected against natural disasters, for instance?
Yes. Yes, this is a good question. That's the reason they postponed that artificial one. They use the real one as the first offshore energy island. This problem should be solved by the construction engineers, not our power system engineer.
But what about the wind turbines, though? They are
Maintenance.
standing alone, right?
Yes, they need to send people use a helicopter or the ships to fix all the problems there, any problems.
Ships?
Yes. You can see that in the figures, there are some port docks. So you just, and also this one should be ready for transfer the hydrogen, produce the hydrogen in these cargoes, the vehicles to transfer this hydrogen to the grid.
Thank you.
Yes. Yes, please.
Yeah, I just have a quick question. I think I'm loud enough. I just have a quick question about this artificial island. So what's the rationale behind building the converter station off the grid and just having like the AC plus 4 and the DC plus 4 on the island? Why the converter station is not on the island? Because it is still offshore.
I think that they have assumed this one by this calculation. For example, this HVDC converter station is already mature. This one is originally from this offshore oil drill platform. They use this technique for this offshore converter station. So if you build this one on this island, it is very, very heavy. Maybe the cost and the space, the volume will be much more expensive than building them in the sea.
And is the connections to the other countries already decided which countries will be connected to this offshore island, or no, it is still?
I think this is the plan with other countries. If you check the report, they mentioned these countries. Where is it? UK, Belgium, yes, they have this interest, but they didn't sign this contract yet. Yes, but that's Bornholm and Island. Which one? This one, this has been decided to connect to Germany. They already have this assignment. You can check this report from Anignet. They mentioned that. The UK one, I don't know. For this one, Germany has been signed. Yes.
Questions? Do we have any online question? Nothing. Okay.
Any questions?
Well, sir, it's good to see that you are advancing your research in the domain of offshore energy, as we all know that the supply chain and the business activities are quite different when it comes to onshore versus offshore. But anyways, best of luck, and we welcome you, especially this is your first time visiting University of Waterloo and first time in Canada.
Yes.
Thank you so much for your wonderful presentation. On behalf of WISE, University of Waterloo, and the entire audience, we thank you from the bottom of our heart. Thank you so very much.
You're welcome. Thank you.